So it's my pleasure to show what we have been doing. Uh, so I hope you can hear me well. Right? Okay. So yeah, so you have already seen this banner, so I can go straight to the talk. So just at the outset, I want to tell you what are the scientific and technical scopes of the beamline. So as Tillman already mentioned, as a multi-purpose instrument where we combine different SAX techniques, ultra small angle, small and wide angle X-ray scattering in a single instrument, and it is optimized for probing the multi-scale structure and non-equilibrium dynamics of soft matter and biophysical systems from sub-nanometer to micron scale and to down to sub-millisecond time range. So this is implemented by means of these technical configurations, combined SAX and VOX, which can go down to the millisecond time resolution, and then ultra small angle scattering using a 2D detector in the pinhole collimation. Traditionally, USAX is done with a Bonsart instrument, which involves a channel cut crystal collimation and analyzer scheme, and it's a scanning method. Whereas here it's like a conventional SAX. So the high degree of collimation in the USAX also makes the beam reasonably coherent. So we can do X-ray photon correlation spectroscopy in the ultra small angle range, complementary to what is done at ID10 beamline. So we can probe equilibrium and out of equilibrium dynamics with XPCS. So the main scientific applications are in soft matter, probing both the equilibrium and non-equilibrium microstructure and dynamics, non-crystalline structural and functional biology, especially probing the structure-function relationship in physiologically relevant conditions, and the same with the functional soft matter and biomaterials, typically structure-function relationship. And then also the beamline is used for industrial R&D, especially involving soft materials. So this can be done on a proprietary level. So in the remainder of my talk, I will show many scientific examples, but I'll be really flashing through them. So in case somebody would like to see more details, they're also summarized in a recent review in Advances in Colloid and Interface Science, published earlier this year. So just if anybody is not familiar with this SAX technique, conceptually it is a very simple technique. A highly monochromatic and collimated beam impinges on a sample, and the scattered intensity in the forward direction is recorded by 2D detector and with the entire flight path in vacuum. So the scattering geometry and the wavelength defines the scattering vector Q here, and modulus of that is given by this simple formula, and it represents the nominal size scales probed in the reciprocal space. Moreover, the measured intensity can be normalized to obtain the differential scattering cross-section per unit volume, and this quantity we normally represent by I of Q, and it contains information about the microstructure and interactions within the sample. So having said that, now I go to the scheme of the beamline, just the floor plan. So you can see here that the optics, the monochromator focusing optics, everything is kept really far away from the sample here, so that we can minimize the parasitic scattering from that, and also collimate the beam. And then the main feature is, as Tillman already pointed out, is this this detector tube, which is about 34 meter in length and 2 meter in diameter, inside which there is a wagon which encloses the different detectors, and it can move from something like 1 meter to 31 meters from the sample. So here you can see the main detectors. The principal detector is ID02 pixel array detectors. This is for SAX and USAX. And then for XPCS, much faster detector. It's IGER 500K. I will tell more about it later. So, I mean, these are the typical parameters which we can achieve with putting two-phased undulators, something monochromatic flux of something like 10 power 13. And with Eiger 500K, we can have a detector time resolution of something like 100 microsecond. And the main feature is this very large Q range. I will come back to that again. And then the high angular resolution obtained at the farthest detector distance. And this slide summarizes, let me remove this one. Okay. So summarizes the reciprocal of the scattering wave vector and the time ranges accessible. So there is overlap between different techniques, SAX, VAX, similarly SAX and USAX. And so we can cover almost 5 orders of magnitude in reciprocal space dimension, and also the Eiger detector offers millisecond time resolution, and with Eiger 500K when go to something like 50 microsecond time resolution. But it's primarily used for XPCS, where such faster acquisition is required. So the beamline alone is not enough to perform research or derive science out of the instrument. So we also maintain a portfolio of sample environments. So the most widely used is the stuff flow device, where we can mix two or more reactants rapidly in the millisecond time scale and follow the evolution of the kinetics. Similarly, most of our work is related to soft matter, so they are soft to touch, and that means their microstructure can be deformed very easily. So coupling a shear cell to rheometer is a powerful approach to probe their structure as a function of applied stress or strain. So we can deform the sample and probe the evolution of the microstructure, or in the simple case, even orienting the sample and enhance the information content in the scattering pattern. In some cases, one can also use hydrostatic pressure to induce the kinetics. For example, using a piezoelectric actuator, one can induce pressure jumps of the order of a kilobar in sub-millisecond time scale. So this can be either used to follow kinetics or studying the structure under different hydrostatic pressure. Then, of course, to enhance the static measurements, SAX or USAX, so we have installed a sample changer. So this is not a typical sample robot used on many BioSAX beamlines, but here is based on a stream selector where we can preload 25 samples and then sequentially measure the samples using a flow-through cell, and with the in-between cleaning and drying operations of the capillary. And in addition, we have a wide range of standard sample environments like heating and cooling stages, electric or magnetic fields, touching device, and in addition, we can easily incorporate user-supplied devices. So to show you the performance in terms of resolution, I use this example. So here it's a scattering form factor by nearly uniform particles. So here the first one is the silica particle. So what you see here is the Bessel functions of and their minima is made by the polydispersity in this case. So you can see that for different collimation conditions in the farthest detector distance, we don't see any resolution effect with the silica particles with polydispersity less than 1%. But if we use, for example, larger particles, in this case, polystyrene particles, size 2 micrometer, and also polydispersity is something like 0.4%. And here you see, again, there's many oscillations what you are seeing here is the 70th order of the Bessel function. And you see with the different collimation condition, we see the smearing of the first few minimum. So the best resolution we can get is something like 2.4 into 10 minus 4. In terms of angular range, this is corresponding to something like 2 microradian, and it is primarily determined by the pixel size of the Eiger 4M detector. So as I mentioned, traditionally USAX is done with Bonds-Hart instruments. How does it compare with the Bonds-Hart instrument? So to obtain this kind of, compared to standard Bonds-Hart instrument, so this resolution is something like 4 times better. So to get a similar resolution with the Bonds-Hart instrument, one will have to use higher order reflections of the channel cut crystals, for example, silicon 555. But then the penalty is that the flux loss becomes prohibitive. But here we can get this kind of scattering patterns within a few tens of millisecond, covering all the entire Q range. So now we are talking about 2 micrometer size particles. So this is also comparable to the size of the cell, for example. So in this case, I show an example of involving E. coli bacterial cells. They are motile cells in suspension. And so depending on the Q range, one sees different features. So at low Q, one sees the entire cell, and in between the ultrastructure of the cell membrane, and at high angles, the details, some structural details within the cytoplasm. So based on this geometrical features, one can develop a structural model to describe the scattering profiles. This has already been done. But what I want to show you here is then what happens at different regions of the cell upon the action of antimicrobial peptide. So what you see here is that, within, below a second, you already start seeing changes at different regions. So using the composite model I mentioned, one can dissect the changes happening at different regions of the cell. So the first is the breaching of the lipopolysaccharide protective layer outside the cell, and then of course the density of the cytoplasm, the membrane, the periplasmic space will be increased, and eventually reaching the cytoplasm of the cell. So what you can see is that this changes the sequence of events when antimicrobial peptides act on the cell. So what you see here is that the eventual breaking of the cell happens at a much later time scale, but inhibition of the growth is already occurring at a much earlier stage before the breakup of the cell. So one can get some kind of real-time information on what is happening upon the action of microbial peptides. So having said the cell, so one of the well-known example is for example, the structure function studies of muscle. So this is the first biological specimen studied by synchrotron radiation dating back to early 70s. So with a highly collimated beam, one can get very well sampled diffraction diagrams from the muscle. For example, in the resting state, one sees this clearly defined layer lines and axial reflections coming from these filamental proteins, the thin filament actin and thick filament myosin. But when the cell becomes active, some of the helical order is lost, and so all this the layer lines becomes weaker, and one sees mainly the myosin based axial reflections. The myosin motor domain is then bound to the actin filament. So by analyzing the changes in intensity and spacing, one can follow the structural dynamics happening at the filamental protein level. But using this high resolution USACs, now one can also follow what is happening at the cellular level. So in this case, it's a sarcomere. So typically in the range of a 2 micron. So what you see is the reflections from in the resting state from the repeat of the sarcomere. But when the muscle is active, you can see that again the reflections become much weaker, and also one can directly measure the change in the sarcomere length from the changes from the changes in the position of these axial reflections. So this turned out to be a powerful method to probe the structural pathway of muscle activation, both in skeletal muscle and in cardiac muscle, especially in the cardiac muscle, to probe what is called the length-dependent activation mechanism. I will not go into more details, but some of the things are we can see in these publications listed there. Having shown some real life examples, now I want to go to more synthetic side. Okay, so just with the EBS, you can see that improvement in the quality of the data. I mean, for example, one can resolve this to very high orders of the reflections of the circumlayer. So now I want to show more of synthetic examples. So for example, the self-assembly, it is an important problem still. I mean, it's many of the fascinating features of the soft matter are due to the self-assembled structure. So probing this self-assembly, especially spontaneous self-assembly of amphiphilic molecules. For example, when one mixes two oppositely charged micelles, so the surfactant, simplest form of this surfactant aggregates above their what is called critical micellar solution, they form this kind of self-assembled structural vesicle, which in this case is a unilamellar vesicle, so only one layer of the membrane. And so this has been studied in quite detail in the past, especially time-resolved Sachs can elucidate some of the details of the pathway of their formation. So with the improvement in the flux with the EBS and also the advanced detectors, one can now look at even much dilute systems. For example, now the concentration is below the critical micellar concentration. So we have a pool of monomeric form of these surfactants, amphiphilic molecules with a hydrophilic head and hydrophobic tail. And then what happens whether they form vesicles or not. So this is typically the evolution of the scattering profile from the very early stage, from a few milliseconds up to 100 of a millisecond. So you can already see that a very large structure is already formed from a pool of monomers within the mixing time of something like 2 milliseconds. So if one analyzes with the conventional Sachs range, it's a bit difficult to distinguish if it's a unilamellar vesicle or some other form. So the Q range becomes important in this case. So if one analyzes the scattering profiles, what it turned out to be that they cannot be represented by spherical scattering functions. They are more like like a tube-like structure. So they form more like elongated tube-like morphologies. And then one can probe, I mean, the structural dynamics. So this kind of studies can be extended to more useful systems which are involved in practical applications. For example, as you know, now lipid nanoparticle formulations are widely used in vaccines. So they involve, for example, Pfizer or Moderna vaccine. So the mRNA is encapsulated by this kind of ionizable lipid nanoparticles together with the helper lipid. And so they can, depending on the pH, they can be a variety of allotropic phase transitions. So one can probe all this by just changing the pH. So in this particular example, what is shown here is this the development of this, I mean, the encapsulation of mRNA upon mixing the ionizable lipid and mRNA using the stop flow. So you can see this peak, which is corresponding in this case to a multilamellar structure. So the mRNA is enclosed in this multilamellar structure. So as a function of time, you can follow how this structure is evolving. So you can see here that the complexation is happening already in the millisecond time scale. So then, of course, one can look at the hierarchically assembled system. So in this case, again, a very simple system involving the surfactant, in this case, SDS, and very commonly available polysaccharide is beta cyclodextrin. And because of hydrophobic interactions, so the tail and also the cavity in the beta cyclodextrin molecules, they form and close to form this kind of a capsule. So this can self-assemble because of hydrogen bonding between the cyclodextrin molecules and form very long-range crystalline membranes. At certain point, they can form closed structures like these microtubules. So in this case, there is a hierarchy of structures starting from the capsids to the the microtube, which are in micron size diameter and many tens of micron long. So from the scattering pattern, you can see the different features. At low Q, one sees the size of the microtube, and at intermediate Q range, one sees the packing of the bilayers, in this case, a multilaminar structure. So one can derive the periodicity and so on. And at higher Q, one sees the ordering within the within the membrane. So in this case, it forms a rhombic lattice. So it's not only to elucidate the structure, but these things can be probed as a function of control parameter. For example, when this self-assembly is induced by quenching the system from a higher temperature to lower temperature. At a higher temperature, the hydrogen bonding won't survive, so they disassemble to simple capsids. So this has been already done, and I will not go into the details. So the details are available in this paper, which is available on arXiv. So now I want to go to my last example, which is involving the coherent properties of the X-ray beam available at ID2. So it's again complementary to what is at ID2. So as compared to dynamic light scattering, so one of the key advantages that we are recording the scattering pattern in the forward direction. So for a given Q, one can see many speckles. So this means one can obtain the both the time and ensemble averaged intensity autocorrelation functions readily from these speckle patterns recorded as a function of time. So with the EBS and advanced detectors, now we can get a speckle contrast in excess of something like 40%. In the ideal case, it should be 100% there, but we are getting very close to that. So this case is just a simple example of Brownian diffusion of a dilute colloidal suspension. So there is nothing strange there. So it just follows the expected, the relaxation rate follows the expected Q square dependence, and the prefactor gives the diffusion coefficient. But now this can be, now that with the high coherent flux and advanced detectors, we can study relatively dilute suspension. So this turned out to be useful, not to look at this passive Brownian dynamics, but to look at more active systems. So why these systems are important? Because they can mimic certain features of more complex living systems. So here, each particle is, in addition to diffusion, they also can be made to self-propel. So in this particular case, we use Janus particles in a catalytic medium. So for example, here, there is one side is coated with titania. So in a catalytic medium, in this case, hydrogen peroxide. So because of the reduction reaction, there is an accumulation of chemical products on one side. So the chemical gradient pushes the particles forward by this mechanism of diffusiophoresis. So now, as a function of the concentration of in this case, hydrogen peroxide and UV power, one can obtain different propulsion velocities. So this can be put in a dimensionless parameter, the Peclet number, which represents the relative importance of diffusion versus propulsion. And then, of course, this can be done in situ just by illumination with the UV light. And of course, nothing happens to structurally to the particles. So what you see is the scattering form factor of these spherical particles. But the dynamics, when the UV power is off, it is diffusive, like the example I showed you before. But when as soon as the UV light is on, and you can see that this is a log scale and the time scale here. So the dynamics becomes, several orders of magnitude faster. And not only that, the spread in this correlation functions here, you can see they have narrowed. So this means a weaker Q dependence. So this is a typical indication of, transition to super diffusive behavior. So weaker than Q square dependence here. By decomposing the intensity autocorrelation functions here, we can get the mean velocity and its variance, effective diffusion coefficient, etc. So this can be, I think I already ran out of my time, but I will just finish in the next couple of minutes. Of course, this can be applied to different type of driven systems. One is when the suspension is under a uniform shear, the same setup I already showed you, the rear meter. So of course, at very low shear rates, still Brownian motion dominates, but as the shear rate increases, the Doppler shifts caused by the shear becomes more and more dominant. So in this case, a constant shear rate, it has a very special functional form. It's a sinc function, the correlation function, as opposed to the exponential decay in the case of Brownian motion. And now we can decompose the intensity autocorrelation function and obtain, for example, how the diffusion coefficient changes in the flow along the flow direction and perpendicular to that. And then, of course, in a more concentrated system, one can apply this to probe what happens, for example, when the system is subjected to a large amplitude oscillatory shear. So then the correlation function displays this kind of echoes. And by analyzing the profile of the echoes, one can get the diffusion coefficient as the system yields. There are lots of details, but I will not go into this at this moment. I think I'm already out of time. So I just wanted to mention some of the recent upgrades. So one of the most recent upgrade is the new control electronics, which is called Maestro, which stands for multi-purpose advanced electronic for sequencing, triggering with reconfigurable I/O. So this allows a very large amount of functionalities in terms of timing, synchronization, and so on. And then the migration from SPEC to the ESRF beamline instrumentation support software, Bliss. And then, of course, the most of the data reduction and visualization is done with the SAX utilities program developed by Michael Strutsky and XPCS utilities developed by William Chavremont, which has also some analysis features specifically for XPCS. And then, of course, we are now with the EBS, the beamline is very stable, but we want to improve the stability of the background, which are affected by thermal drifts. So we are replacing most of the supports with the granite structures so that thermal drifts will be minimized. So until now, we are still continuing with the focusing mirror from before the EBS upgrade. So now we will have a new focusing mirror, which is more adapted to the EBS properties. And then, of course, we will replace the wax detector again with a ESRF developed SmartPix 1M detector, which is based on Medipix 3. And then, okay, we will also have a fast detector for XPCS, so the Rigaku XSPA. So this is funded from the BF project of Christian Good, which is shared with ID10. So we hope to have these developments in place by next year. And then, of course, we also want to do more into the SAX analysis, especially we haven't made any progress in this respect, but sooner we want to get into machine learning accelerated SAX data analysis, especially trying to do reverse engineering of the SAX data to get more real space information. So then, of course, all this won't happen without the people. So my colleagues represent the team and also those who provide support. And then, of course, we need to thank a very large number of people, and the list is certainly incomplete. And then I already run out of my time. So I will not read all the summary and outlook, but I'll be happy to take any questions if you have. So thank you for your attention.
Thank you very much.
Thank you, Narayan. That was a great talk. I would encourage the audience to write their questions in the